So, thanks. We're pleased to have Ankit Goyal joining us. Ankit Goyal is a senior research scientist at NVIDIA. Has been working with Dieter Fox and done a lot of great work on robot learning, vision language action models, and vision language action models without specific modifications to the architecture for actions. So basically using VLMs for actions for robot learning.
Okay. Thank you so much for the introduction. And thanks everyone for having me. I'm really excited to be here. I'm Ankit Goyal, a senior research scientist at NVIDIA. And I'll be talking about my work in building the foundations of generalist robot learning. So let's dive right in. So for decades, robotics was dominated by the specialists. Right? So these are robots we see on the factory floor, where the environment is fully known and controlled. Every single movement is pre-programmed, and these robots execute them with superhuman precision, day in and day out. But the specialist robot is rigid. Even a slight change in the environment and the robot fails. On the other hand, we have long imagined the generalist, a robot that can work alongside us in our homes, our hospitals, our warehouses. But these are unknown environments. Every home is different. Every hospital is unique. The generalist is expected to not just perform one task, but all the tasks that humans do. The generalist task cannot follow a fixed program. And the generalist must be generalizable. It should be able to handle new objects, unseen tasks, and unstructured environments. The goal of my research is to build the brain of this generalist robot. And as you can imagine, this generalist brain unlocks massive applications across domains, from caregiving to construction to keeping our everyday spaces clean. But how do we actually build this generalist brain? Fortunately, we don't have to look far for the inspiration. In natural language processing and computer vision, we are witnessing unprecedented generalization. Systems like Claude Code can write and reason about code. Models like Sora can generate photorealistic videos of scenes they have never seen before. And all of this has been unlocked by the use of foundation models. But when we look at robotics, the picture is very different. We are far from the generalist robot. Robots struggle with tasks that seem trivial to us. They are unable to handle or recover from even seemingly simple small changes.
You too.
This begs the question, can we leverage foundation models for building the generalist robot? I began exploring this question a few years ago, at a time when this was not the mainstream direction in robotics, and today it has become the central question in the field. But using foundation models for robotics is not straightforward. There are fundamental questions that we must answer first. We start with the foundation model. This is trained on a large amounts of data on internet scale, language, and vision data. This foundation model can predict text and images. But a robot needs physical actions. It needs to move an arm, it needs to grab an object, it needs to navigate to the next room. And naturally, this leads us to the first very basic and fundamental question. How do we get a foundation model to plan or predict actions in the physical world? The foundation models we have are trained on internet scale 2D images. But robots live in the 3D world. They have access to 3D sensors. And this leads us to the second question. How can we take 3D as input to these foundation models, specifically in the case of predicting actions? And the third, decades of robotics research has developed specialized components. We have Matt in the room, like motion planners, compliant controllers, or specialized learned models. These are proven, reliable, and safety critical. And this leads to the third fundamental question. how can we leverage these specialized components alongside the foundation model? My research has addressed all these three fundamental questions. And in this talk, I'll focus on one work on each question. And by the end of the talk, I hope that you will have a general understanding of this very exciting field of robot learning with foundation models. So let's get started. So the first question is, how do we predict or plan actions using a foundation model? So before going into that question, let's first try to understand what it means to predict action in robotics in the first place. So a robot, a very simple robot, it's a very simple robot here. It has multiple joints, and each joint has a motor. To move the robot, we have to set the angle of each and every joint. This is done by setting this motor, right? So this is the vector that we are predicting. So for the purposes of this talk, we can assume that predicting action in robotics means that predicting this joint angle at each time step. So that's an assumption we can take for the purposes of this talk. There are other kinds of actions, but that's like the simple one we can assume. Now before we can predict an action, we need a foundation model to begin with, right? And for this, the vision language models, or VLMs, are a natural and primary choice. So the VLMs take image and text prompt as input, and they produce a text response. They are built by taking a large language model and an LLM and adding the visual understanding capability on top of it. But VLMs produce text. They don't produce actions. So the key question becomes, how do we convert a VLM into a VLA, or a vision language action model? Now, in order to understand how to add action, let's first quickly review how does a VLM works. At the core of it, a VLM is a next word predictor. Given some words and an image, it predicts the next word. So let me give you an example. So we start off with this image and a textual instruction that describe the image. The first step, we convert this image into vectors using an image encoder. So these are a set of vectors that represent this image. In the second stage, each word is also converted into a vector. And this is done by using a lookup table. So we can almost think of it like an embedding to vector dictionary. Think of these vectors as internal representation of the word that the model has. These vectors are then fed into the core processing layers of the model, which are called transformer layers, that predict the next word in the sequence. In this case, it could be there. The predicted token is then fed back to the VLM, and that's why it's called autoregressive. And it predicts the next word in the sequence, for example, is. This token, again, is fed back to the VLM, and it predicts the next token in the sequence, which is a. This is autoregressive generation. The VLM is predicting one token at a time. For clarity, I'll place all the predicted tokens on one side. Now, how do we create a VLA from it? We take the same VLM architecture, but instead of using a general image description, we provide the VLM with an image of the robot scene, and let's say a task description, pick the game. Right? So we are essentially copying that entire network below. The question now is, how do we predict actions? So the existing approaches in literature can be classified into two categories, the first being discrete action VLAs. In this method, we take our continuous action values, let's say between xmin and xmax, and then we discretize those values into fixed number of bins. We represent these bins with symbols that we call action tokens. Then we override some of the existing tokens of the VLM with this action tokens. Right? next.
So why override? Why not just add new tokens?
Yeah, we can also add, but like that's like the what some of the approaches do.
And can you explain? So action here is a single real valued number. I mean,
so the action we have like the entire range of, let's say, actions. So in those we have, let's say, going from x min to x max. So for example, degrees going from 0 to 360 degrees.
But you have a vector of different angles.
Yes, we have a vector of different angles, but let's say all those dimensions we can normalize and get like one consistent bin. Okay. Coming back here, now we can override, or we can, as pointed out, we can also add these new tokens in, and then what we do is now we'll, instead of predicting text directly, we'll train this network and fine-tune this network to predict these action tokens. Right? But as you can see, this approach has two problems. The first being, we have a limited number of bins. Since we are doing this discretization operation, the model can only represent a limited set of action values. This leads to low action resolution. And such a model will lack the fine-grained control needed for very precise motion. Right? And the second issue is adding a new action token disrupts the pre-trained vocabulary. The model was never trained with this token, so we risk losing some of the inbuilt visual and language understanding of this model. Let's reset the VLM again. And this leads us to the second category of methods, which I classify as action head VLAs. Essentially, what we'll do is we'll attach a neural network that takes in vectors from the VLM and produces new action. This additional neural network is called an action head. But the action head needs its own architecture, and it needs its own training recipe. Right? For example, how large should the action head be? How should this action head be trained with relative to the VLM? These are additional design choices that emerge when we go with this approach of adding a new action head. The question we ask is, can we build something better? Something that doesn't have any of these limitations. It doesn't have low action resolution, doesn't change vocabulary, no new neural network, no additional complexity. Can we build something like that? So let's relook at what predicting action in robotics means. Right? So the question is, how do we now predict these actions in a way that doesn't have these limitations? It turns out there is a surprisingly simple answer that addresses all these limitations. Can someone point that out? So let's, probably Matt knows already, but let's look closely at our actions. How about we represent this action as text and train the VLM to natively output action as text. This will maintain the high action resolution because numbers are compositional, and we can ask the model to predict actions to whatever number of significant digits we want. This will not change the vocabulary. Numbers are already in the vocabulary of the VLM. It would require no additional neural network. The VLM already knows how to predict text. And this method can be trained or fine-tuned exactly as we are fine-tuning the VLM. So it's very easy to use and very easy to train. We call this method VLA0, a VLA with zero modification to the VLM. And here is a schematic representation of VLA0 in action. It takes in the user's instruction, in this case, place the cupcake in the bowl, and the camera images input. The VLA0 then predicts the next set of actions as text. The predicted action is fed to the robot, which updates the scene, and a new image is generated, and is fed back to VLA0. VLA0 predicts, and the VLA0 predicts the next action. So it's like a closed loop system. You have a question?
Is it also fed the previous actions?
Not in our design, but you could easily do it. So even though this idea is very simple, it's actually pretty effective. In fact, this very simple design outperforms all alternatives, including state-of-the-art VLAs like Pi0 from Physical Intelligence. And it shows that the simplest design, an unmodified VLM, is actually a powerful way to represent actions in foundation models. Note that VLA0 is not pre-trained on any large-scale action data, and it still outperforms popular methods that are pre-trained on large-scale action data, like Pi or GRUD from NVIDIA. And this surprising result demonstrates the strong representative power of this design. Yeah.
What is the time resolution here? Like
How
what time does each token?
So we are predicting at 15 hertz. So each action would be at least a 15 hertz time distance, and that could again depend on the data set, on the setup, and we can train the model accordingly.
And that's the case for all of these models.
That's the case for all of these models. So everything is like fair in that the action is exactly the same, the benchmark is exactly the same.
So is the main distinction here basically just how you tokenize numbers? Like in the case that you mentioned before, where like you introduce a bunch of action tokens, which basically correspond to, it sounds like numerical values. Is it not just that here, instead of introducing new tokens, you're just using whatever native number tokens are in the pre-trained model?
Yeah, exactly. That's the main difference, and it's also the advantage is not changing the vocabulary of the VLM. So the VLM already, let's say, has some representation of numbers, and it knows that 1 + 1 is 2, and all those capabilities just directly come through in this design because they're not overwriting it.
Sorry, I follow up. So a single action though consists of multiple tokens, right?
Exactly.
And so how does, maybe you'll get to it, but I'm curious about the inference trade-offs, the inference time trade-offs.
Yeah. So the inference time trade-off here would be because we cannot predict. So we have to predict these numbers. So now we see, let's say, in order to predict one action, we have to predict, let's say, 4 numbers. So it will be 4 times slower as it does for inference.
There must be some training here. I mean, you said there's
Yeah,
no
there's
large
training.
scale. Are you going to talk about the
So all these models are trained on
on actions?
On actions, yes. So nothing works out of the box. All these models are trained.
You said no large scale.
Yeah, there's no large-scale action pre-training. So like some of these models are actually pre-trained on a large-scale action data, which is separate from the test data set here. But this model is just using the VLM and no pre-training of a large-scale action
But you
data.
will talk about the training.
Yeah. So here in the first case, essentially all the models are trained from scratch with just the VLM.
How big is the training set?
So this training set would be around 2,000 demonstrations.
2,000 demonstrations.
2,000 episodes.
Okay.
And this is not in simulation. These are actual.
So this result is in simulation. We have the same result. We also see the same result in the real world.
What's the difference between the model sizes, roughly?
So all of these models are around 3 billion parameters. And some, I think ours is 3 billion. There are some models which are like 7
So yours is 3 billion as well.
Ours is 3 billion as well.
Model
It's the
size
same
is
VLM,
Okay.
and some of them are also using the same VLM back.
Just one more.
Yeah.
So is the training data all pick and place, and how varied is the object?
Yeah. So here the training data is like pick and place, opening drawers, very simple tasks, pushing things around. So that's like the training data, and the in these environments, the variability is in where the objects are moving. So you will have like new poses of objects.
How varied are the
Yeah.
objects?
So the objects themselves are not varying between training.
How much in the pose?
They're all cupcakes?
So no, they're not all cupcakes. So this is like a standard benchmark called Libero that's been tested on. It's like very popular for testing PLA.
But there's very little variability in the pose of the object. The cupcake is, here plus or minus, I think it's like a couple centimeters, right?
I think there would be probably So when we test it in the real world, so we are wearing it in a 1x1 meter kind of a setup for testing in the real world. The simulation benchmark is like a fixed benchmark, so we don't touch it. That whatever variability it has, all the models are using the same thing.
There are issues with Google, but Tinchon can tell you.
Yeah, there are definitely. I agree. There are definitely issues with, and we need like better benchmarks which are really testing like outcomes.
Because the action distribution has to fulfill the constraint of control loop, control dynamics, closed loop control dynamics equation of the actual robot that it is.
So here, since we don't do any extra post-processing on that. So it might give you an error, or it will say fail if it is giving something which is like, so that's, you don't post-process or control. So that will be like registered as a freebie.
I thought the point of PI-style action hat, diffusion hat is about latency.
It's about latency, and as well as like for also generalized, like it's like one design of making things. It's not necessarily just the latency. We also want to capture multimodality with that design.
Right here, you definitely have multimodality, but when you use LLM decode, your latency really cannot compete with the diffusion hat.
Yes, but the advantage is that what PI style design does is that since you're back propagating throughout the VLM, they self-report the language understanding is really suffering a lot. Here, I have like some words that I will talk about later, but when you represent things as action, the language understanding just remains completely intact.
Is it just kind of coincidental here that you don't need that many tokens to encode an action, and that's why this is beneficial? I mean, if you were to encode images this way, of say just sequence of numbers that is the intensity of every pixel, it seems like it might not be a great
Yeah, it might not
choice.
work for images.
So,
but it works for actions because actions are much more condensed in the sense you have to predict fewer numbers.
doesn't that depend on the complexity of your robot or controller?
You're right. It depends upon the complexity of the robot, but then every method has to do that. For example, the diffusion method is like a bit less, but like for the discrete action head VLA would have to also do the same thing. It has to predict multiple actions. It has to predict like multiple numbers for each dimension. So let's say if you have, let's say, a 20-dimensional degrees of freedom, then it has to predict 20 numbers.
Yeah, but you're making a choice of not learning an encoder. I'm just questioning whether that's a general, whether that's kind of coincidental you can get away with it in this situation.
It's a good question. You're right that there could be scenarios we might not get away with it. Something we don't test it here. But you're right, like if it is like very high dimensional, then there might be problems that is not surfacing at this level. But even this is not solved, so I think it's still a good problem space that we can solve first, and then probably even like more higher dimensional matrices.
Have you tried just like a Dino plus an MLP for these tasks? How well does that work as a baseline?
Dino plus MLP, I think it will be close to the diffusion policy, the first method here. It's also like a ResNet and a diffusion net at the end. So I guess like similar to that.
Because we found it works pretty well on Libero.
Yeah, so I
Very
think
similar to state of the art on Libero.
I see. Yeah, I would guess it like I would range it around like the diffusion policy, which is the first method. Okay, those are all great questions, but let's move ahead. So within just like 4 months of release, it has been organically used by the community. So for example, this VLA0 TRL uses VLA0 to create like a lightweight code base for building like state-of-the-art VLAs. And it's another example is VLA0 small, which creates a very simple VLA code base for education and experimentation. and VLA0 because of its real simplicity. It's like lowering the entry barrier to VLA research. So I don't see it like a end-all solution, but it's like a very simple baseline that people can try. And concurrent to our work, more methods are now being developed with this paradigm of action as text. Great. So we address how to predict action specifically for this low-level motor control. And there is another fundamental problem in robotics, which is called long horizon planning. For example, imagine the task of warming a salmon for dinner, and it would require you to plan at a much higher level, deciding what to do next. And the question we ask is, can we leverage foundation models for this kind of task planning as well? So I won't go into a lot of details here, but very briefly, we studied this question in our work prompt. And the key insight is that we need an effective way of using LLMs for planning. You need the right interface between the language model and the robot. And it turns out that code, specifically Python program, is a great interface that you can use. And since its release prompt is like the standard method for this field of foundation model-based planning in robotics. So with that, we have now covered the first part, which is essentially how do you predict or plan actions with the foundation model. Okay. So now let's move on to the second question, which is how do we take 3D as input to the foundation model? And why do you care about 3D as input? So robots need to act in the physical world, which is 3D. And robots have access to 3D sensors. So for example, sensors like Intel RealSense, which would give us a 3D point cloud of the scene. And hence, the question is, can we leverage these 3D sensors by encoding the 3D information and feeding to the foundation model? So one approach that existed in the literature is to divide this 3D space into a small number of cubes called voxels. These are essentially 3D pixels. But as you can imagine, this is very computationally expensive. It's doubling the resolution means we are increasing computation by 8 times. The cost is like cubic to the resolution. So voxels generally don't scale well for high resolution needed for very precise manipulation. The other approach would be to directly encode the point cloud. But a point cloud is just a set of unordered points. There is no grid structure inherent in a point cloud. In processing point clouds, and processing this unordered set of points, it requires specialized architectures, like for example, PointNet++, which involves like custom designs of how to group the points, how to extract these features and propagate these informations. And encoding point clouds is generally an involved process, and it requires custom engineering. Given this, we ask, can we do something better? A strategy that is more effective, more efficient, and also much simpler.
On the voxel point, did you try the same way that fMRI does, how they represent the voxels, and like they do the fast Fourier transforms, and complexity can be reduced to like n log n rather than...
No, we didn't try it. So some prior methods tried it, and they were using this the perceiver trick. Essentially, you will have the tokens, but you will have processing. You will to cross attention have processing on a fixed number of tokens, but it's still very expensive. I'm not sure about the one that you mentioned. Okay, so can we do something which is more effective, more efficient, and simpler, right? So a key insight comes from engineering drawings. So in engineering drawings, we have always had something called orthographic projections in 3D. So think of them as images of the top, left, and front view of the objects, and they are used to represent the 3D object themselves. Specifically, given a point cloud, we take the same approach, and given a point cloud, we render it through this set of orthographic images. So I'm showing some orthographic images for illustration here. Note that these are not real cameras. So these are like analytical cameras, so we can explicitly, using mathematical rendering functions, we can compute these projections or images from the 3D point cloud. Now, because these are just images, they can be fed to any existing vision model. This means that we can leverage all the rapid advancement on the vision models, including foundation models. We tested this simple idea on point cloud classification using just off-the-shelf vision models at that time, which was like ResNet. And this very simple method outperforms state-of-the-art point cloud-based methods like PointNet and PointNet++.
What's the task here?
It's a point cloud classification. So given a point cloud, you have to classify it into some fixed number of categories.
How are you dealing with? So right now, to generate these views, you have a single real sense camera. Or are you moving you're doing a nerf, Gaussian splatting?
So these views are these point clouds are when we tested on this, these point clouds are already given, so we can assume them coming from some sensor. So we don't touch the sensor.
But what you're showing, there are no occlusions. There are no holes in the images that are generated.
Yeah. So here that image is just as I was mentioning is for illustration. But when you're doing rendering, we can do things like Z ordering and stuff, which takes care of order of the point cloud, and they're like standard rendering pipelines that take care.
But you will have holes in the image.
Yeah, there might be holes in the image,
Okay.
and the network is supposed to take care of
Okay.
when you train the network.
Do you have any examples of actually rendered point clouds?
Yes, I do.
Okay.
In the next slide. So this is one of the real point clouds in one of the simulation data sets. And this idea is equally effective for robot manipulation. So in our work, robotic view transformer RVT, we take the 3D point cloud from the robot scene and render these orthographic images. And these are like the actual renderings, or the kind of renderings that one can see from the pipeline. So you'll see that the black things are like where there is like no points at all.
Are these synthetic?
So this is a simulation.
Then real, it depends on how you get the point clouds, but the real point clouds would be way sparser than this, presumably.
You are right. They would be way sparser, but the strategy works in things.
So you end up with images which have a lot of holes, like most pixels probably are holes, and then still you classify better than PointNet.
No, not classify better. So that's like a different work. We test it in robotics with those images, and it works pretty well. We can
But the plot you just showed in the previous slide, that's classification.
That was a different work. That was like a classification.
Okay.
That's like separate. There's no robots there at all.
Okay.
So that was a work in computer vision, and that's called simple view. But the inspiration comes from there. And then what we can do is we can feed these images to any image processing transformer to predict actions. So note that in RVT, this model is initialized from scratch. There is no foundation model there. This is just like a standard model initialized from scratch.
Did you try reconstructing the point cloud from the orthographic images that we have? Like, is there a loss of information? And in the setting that while we are doing, is there a reconstruction loss?
We don't necessarily test it.
It's working well, so it's good.
Yeah, I don't necessarily. But like we test it in real here. Sorry, but
If the way you use point cloud is to render it as images, then why not just take 6 cameras and just use vision?
yeah.
So you need 3D.
Yeah, so if you use, so there are multiple issues with that. One is that when you use, like, let's say, you would need to place 6 cameras. It's like a very difficult setup. For example, placing a camera right at top of the robot to get like the top view is pretty hard. So that's like one issue, like a practical issue. the other issue is that once you do calibrate, but this method will work with even single cameras. So all these are working with a single depth camera. So that's one thing. The other thing is like, if with this method is that you can move your 3D camera around, and as long as you have calibration, the method will still work because you are re-rendering these views. But with real cameras, if you move them around or if there is even one camera drops, then the method will complete.
For all the tasks you're showing here, what's the randomness, like initialization or the target? What is fixed? What is?
Yeah. So like these, so there is no foundation model here. So everything here, the changes are like the examples as I show you. So for example, in one, this drawer would move around and the objects would move around. So that's like the randomness in the training test.
So there's no foundation model, but what's the base, like transformer
Yeah,
diffusion?
a standard transformer with just attention loops.
So if the motivation here isn't to plug into a 2D foundation model, why not use some efficient sparse 3D representation in terms of like quad trees for voxels, meshes, or convolution over the approximate surface of a point cloud, instead of doing 2D projection, which eventually loses a lot of information.
Yeah, so I'll talk about like we actually feed it to the foundation model. It's not being fed here, so it will so there is eventually we do feed into the foundation model. Okay, so like this strategy is highly data efficient, and with just 10 demonstrations and these like variations, we can learn a policy, and this model is like order of magnitude faster than the other method that existed, while also being much better at performance. The other method was like voxel based, pretty popular method called Paract. It turns out that we can make this design even better. So in RBT2, we extend RBT with a multi-scale design to improve action precision. So we have the coarse branch that processes the point cloud and identifies the region of interest. And then we have the fine branch, which zooms in into the region of interest and re-renders new images and feeds those to the transformer to make precise prediction about the next action location. And finally, based on the region with the highest score, we look up the features, and those are then passed finally to a neural network to make predictions. So I won't go into a lot of details here, but apart from the multi-scale design, there are other key improvements. For example, we use a custom CUDA renderer for fast orthographic rendering, so we get like 3x speed up as compared to like off-the-shelf PyTorch 3D renderers. And also we use some special upsampling layers to increase feature resolution, which saves on memory as compared to like standard upsampling layers. And together the RBT1, RBT2 series of work improve performance and also reduce training time and by an order of magnitude and increase inference time over what existed in robot-level. And with the same setup and with just 10 demonstrations, for the first time we could solve like tasks which really require like millimeter level accuracy. For example, if the plug is slightly off, this will not work, and we can solve these tasks with the variation with just 10 demonstrations.
Here the input is just vision. There's no tactile sensing, no force sensing.
No tactile sensing. So it's like pure vision prediction. And now, as coming back to that point, we can take the idea one step further. So instead of using a custom neural network, we can use like a VLM to feed in these images. And a method called OGVLA, it can learn new tasks from just like 3 demonstrations succeeding, where like if you have state-of-the-art methods which don't have this 3D as input, they will have almost 0 success rate. And this RBT has been widely adopted by the community, and it's like has become like a standard component in state-of-the-art 3D aware manipulation policies. And here I'm showing like some examples And further, similar to OGVLA work that I showed, recent foundation model-based manipulation policies are using like this, the RBT trick to take 3D as input. And it's also state-of-the-art models. RBT and the models which are built on top of RBT are state-of-the-art across all major 3D-aware manipulation benchmarks, including RLBench, Arnold, Pelosian, and Generalist. So that brings me to the end of the section on the second question: how do we take 3D as input to the foundation? So now we have an end-to-end foundation model that can take 3D as input, and it can predict actions. The question I ask is like, is that the best we can do? Like this end-to-end monolithic foundation. We thought about this question and argue it's not the case, right? Let's look at how modern LLM works. So the LLMs are not monolithic, right? In other words, the end-to-end neural network is not doing everything. The LLM leverages external tools like compilers, calculators, or search engine for better performance. Similarly, in the case of VLAs, decades of robotics research has produced powerful tools for like compliant controllers, motion planners, or specialized learned models like RBT. And the question we ask is like, just as LLMs are leveraging these external tools, can we also leverage them in the context of VLA models? So in this next section, I'll focus on this question of how can we leverage specialized tools alongside the foundation models in case of robotics. So you might ask, like, we want to leverage specialized tools, but are they actually needed? And the answer is definitely. Like, we definitely need specialized tools, and let me show you how. So here is an example of a monolithic VLA, which was state-of-the-art at the time when we were doing this work. It's called OpenVLA, and it was. If you can see, the action predictions here are not very precise. It often makes action predictions that are like imprecise, and then it's also like clunky. But how can we make the VLA more precise, like produce like really precise actions? Right? Is it something we just saw we can use?
Sorry, that's your data you were showing here, the OpenVLA?
Oh, that's from the.
Okay, so it's been fine tuned on that domain.
Yeah, it's like by the authors themselves.
Okay.
So yeah, so the question is, how can we make the VLA more precise, right? Like recall, we just discussed RBT2, which gives very precise actions. It was able to like plug things into the software. Could we leverage this specialist model? We could, but how? Like, it would be great to leverage this model to make precise predictions, but how do we do that? And this is exactly what we study in this paper, in this work called of hierarchical in Hamster, where we propose the idea of hierarchical VLAs for the first time. So it's essentially a two-stage pipeline. So in stage one, the VLM takes in the foundation model, or the VLM takes in RGB and a task instruction to predict a high-level plan. Right? And this high-level plan essentially serves as the interface between the foundation model and the specialist model. And in stage two, we take our specialist model, for example, RBT2, which will take this high-level plan and will take this 3D observation and predict actions. So this gives us a clear hierarchical structure between stage one and stage two, right? Once we have this high-level plan. But the key question is, what should this plan look like? It should be something that the VLM can output, and something that the specialist policy RBT can consume. Right? So what could it be?
So why do I need, look, you put the banana on the plate. Why do I need to decompose this input? It's not too different than put the cake in the bowl, right?
Yeah.
Why do I need hierarchical models for this? If it was, slice the banana and put it on the plate, then I might want something like that. But this is just an example.
This is just an example, and it's talk more about the design itself. It's just giving an example of a task and the pipeline.
Okay.
Yeah, that's a good suggestion actually. This example is not great. Okay, so like coming back to the question that we have, okay, what should this interface be, right? How about a 2D path? So we know that from VLA0 that the VLMs can naturally output action as text, right? How about the VLM outputs a coarse 2D path, a rough trajectory of where the gripper should go directly in text? We know that is something we can do, and then we can overlay that prediction on top of an RGB image, and any specialist model, for example here RB2, that can consume that RGB image and can use that plan directly. So this design provides us the best of both worlds. So we get, like, let's say, complicated language generalization from the first part, and we'll get action precision from the second part, which is taking care of the actual action prediction. A further advantage of this design is that we can improve these two stages independently, and the overall system can benefit. For example, if we improve the stage one in some way, then without changing the specialist model, it can improve the overall performance of the system. So because the foundation model in first stage only needs to predict this coarse 2D path and not the precise action, we can train this foundation model not just on action, but on any large-scale, even non-robotic data sets of like human videos doing the task, or even imprecise simulators for this.
So sorry, maybe I missed it. So RBT2 is reasoning over the three orthographic views.
Mm-hmm.
So here you have a rendered 2D view. How are you making sure that it's consistent across the orthographic views?
So once we make this plan, we just splat that onto the 3D and then re-render it, and RBT takes care of it. How do
you project this into 3D? Because it's not all the points are on the table.
Yeah. So if some point is, so there are like actually two strategies of doing it. So one is like the points that we just splat the point in the direction of the camera. Mm-hmm. So it will splat at some point, which is at a different point. So there is let's say no 3D point there, but it will project onto the
somewhere in midair.
In the and that's one strategy.
Yep.
The other strategy is actually which we call the concat strategy, which I don't show here, is RBT can take language as input. Now it learns with this 2D path, 2D path predictions directly, because RBT can also take language as
input. The 2D path on just one of the images.
On just one of the on just the input image.
Input image. Okay.
Okay, coming back to our VLM, and then this VLM can be trained with like large-scale data, and like coming back to your question, it actually, and because it's predicting directly in text, it actually shows great generalization. So for example, this is the task, like put the cup in the cup holder. That's only seen in simulation, but the VLM will work zero shot on a real image, for example here, and surprisingly, it will also work very well on something as abstract as a sketch. So let's think about what the VLM is doing. So the VLM has learned to predict trajectories from the simulation data, and it has never seen anything for a sketch in its training data. But the VLM understands sketches from the diverse internet scale data that is as seen. And it's composing these two separate pieces of knowledge, composing this knowledge in a way so that we can make these kinds of predictions. So this gives us like this remarkable generalization. Here is another example, screw the light bulb, which is only seen in simulation.
What does the color on the path mean?
So the color on the path is actually the progression of the trajectory. What's the starting point and what's the end point?
Does the VLM on the previous slide take in all three orthographic views as input images as well?
No, the VLM is just taking the primary image. So the VLM is not taking the orthographic views here.
Okay, so what you're adding in this second stage then is the projection onto multiple views. So it's the rendering plus multiple views. But
so the second stage has access to the 3D. So here the second stage has access to 3D. So it can be whatever pipeline it needs to be. So here RVT2, and it will do that orthographic projection, whatever it needs to do. The first stage is only taking the provided image.
if you provided all the images that you're using in the second stage, the first stage, would you still need the second stage?
Sorry, I
If you
didn't.
provided the additional image in the second stage as input in the first stage, would you still need the second stage?
You provided.
If you provided the multiple.
So that's a different method. That's like the first OG VLA method. That's not hierarchical. In this way.
You need to get the actions somehow, right? This is the idea.
Well,
The first stage is just outputting a path in the image. You'd have to get it to output actions, which could do like the VLA0 like approach.
there seems to be information you're adding in the second stage that's not input to the first stage. And there's an issue of level of detail. If you added all the information in at the first stage in terms of all the 2D context, would the second stage still be necessary to refine the plan to an action, or could you accomplish this once?
So you could have like a monolithic approach where you add, let's say, the 3D to the first stage, but you'd have to do all the things that we did in the first set of works. But in this set of work, the VLM, since the VLM natively does not take 3D as input, we keep it to just take the provided image. So that approach will not be hierarchical.
Right, but you can provide 3D as multiple 2D views. So are you providing those multiple 2D views as input to the VLM here, or just one 2D?
So we are not providing it here, but you're right, there is an alternative, which is to also provide that. That's not something we test in this. So you're right. So there is an alternative to that, but we don't test it here. 5 minutes? Okay, yeah.
We're asking you a lot of questions. So
That's
we're
great,
slowing
actually.
you down.
That's great. Okay, so I talk about the generalization here, and also like more generalization we see, like for example view consistency that directly pops out because we are using the VLM backbone. It's like pretty hard to get like these kinds of view consistent prediction if you're just doing like robotics specific data sets. And then as expected, this approach is better than either just using the first stage or just using the second stage. So we compare this hierarchical approach to just training on this, as one of the questions was just having like a monolithic VLA or just having like the 3D ones. And then so this was like one of the very first hierarchical VLA designs, and like major labs have like now independently converged to a hierarchical design, including Helix from Figure Robotics, Group from NVIDIA, and Hyro with like different interfaces. So for example, Felix would use vectors to communicate, or Phi would use language to communicate. And beyond just manipulation, this hierarchical design could be used in other tasks, like in navigation, where we could like have a high-level plan. For example, in Vamos, they use a high-level first stage and then use a local motion controller at the second stage. Or you could like also play with the interface itself. So for example, Peak that uses a mask interface along with the along with just the so that covers all the three sections that I wanted to cover, and I've also built towards the goal of robot learning from other perspectives that I want to very quickly highlight here, given the time constraint. So we know that simulation is very crucial in robotics, and I've done work in like simulation-based data generation and evaluation. For example, I would like to highlight this work called InfiniGen, where we create these fully procedural, close to photorealistic 3D worlds that can serve as like almost infinite training data for a lot of 3D vision tasks. Similarly, I've done work in manipulation beyond what we discussed today. For example, ManiFlow, which is one of the best performing models that takes 3D as input and does dexterous manipulation in non-foundation model setup. And I've also done work in like 3D vision and neural network design, one of my works being like non-deep networks, where we build low latency performant networks that are not very deep, which are particularly useful. The low latency is particularly useful in robotics for like edge predictions. So beyond the research contribution themselves, I've had educational impact, like several of my works are being discussed in graduate courses. And as someone who has learned from papers like these, seeing my work on the other side is one of the most rewarding part of my research journey. So what's next? So last 4 minutes, I want to talk about what's next. So how do we build this generalist brain? So let's take a step back and revisit the specialist versus the generalist paradigm. As a reminder, on the one hand, we have the specialist on the factory floor pre-programmed, and on the other hand, we have like the generalist that can supposedly, hopefully, do any task in our homes. Advances in robot learning moved us beyond just the specialist. So we have these learning-based methods that can handle some variability, like for example, as I was showing, like changes in object poses. But the generalization was limited. Like these methods would fail when seemingly small changes in lighting or rephrasing the instruction, or when we have an unfamiliar object the system would create. Some of the research that I've done has helped us leverage foundation models. And as addressing some of these core questions, we have seen a step up in generalization. So the systems now have improved generalization to language instruction or like new objects of visual changes, as some of the VLM examples that I was showing. But we are still very far off from the goal. Like current systems work in labs with like modest performance, and I believe several breakthroughs will be needed to actually take these robots from lab to home that can like reliably operate in everyday environment. And to achieve this, we must address, I believe we must address three open questions, and the three more promising directions are around like reasoning, architecture, and data. So let me quickly discuss them one at a time, starting with reasoning. So if you look at model VLM LLMs, reasoning has been a big unlock. It's a chain of thought, self-correction, iterative refinement. All of these things really drastically improve the performance of the model. So the question is, can we give robotic foundation models similar capability? And what would reasoning look like in the physical world? So consider the task of the robot packing objects in a box. So the robot would need to reason about the 3D geometry first, right? It would need to decide what orientation, what sequences avoid collision. It would need to self-correct itself. And this kind of reasoning, I would argue, requires 3D as the medium of thought. So my goal would be to build robotic foundation model that have like similar to language-based reasoning, have this kind of 3D reasoning, essentially manipulating the 3D world and iteratively updating its model before making a prediction. Second, on architectures. So today we can identify there are two prominent paradigms for architecture for robotic foundation models. One is like VLMs that provide powerful semantic understanding, common sense, but they don't have like an explicit model of the dynamics of the scene. On the other side, we have video generation models that are more explicit on dynamics, but the semantic is opaque and they are also not very efficient. And beyond these paradigms, there is another critical gap, as came up during our discussion, is there are other rich sensory modalities like force, touch, which are essential for manipulation but are completely absent from foundation model designs. My goal is to establish the right architecture for physical understanding that will combine like the semantic efficiency of VLMs with the learned dynamics of the world video models, as well as integrating it with rich sensory signals. So in Hamster, I already showed that hierarchical design that where we have components reasoning at different levels could be very useful, and I plan to extend on that principle to have robotic foundation models that have these components that can take full range of sensory modalities as input. And third, data. So in AI, we know that data is the single most important ingredient. The success of LLMs and VLMs has shown us, but where is the internet scale data for it? I believe there are two very major sources. One is like human video. So in Hamster, we showed how we can use coarse 2D trajectories to train, but the signal was very coarse. So we need to build pipelines that can extract rich signal from videos. So like, for example, dexterous finger movements or tactile forces or contact events. And I call this as like inverse robotics. We are essentially inverting the robotic pipeline to recover the actions from the videos. And the second source of data is simulation. A simulation can generate unlimited interaction data, but it suffers from two key limitations. One is the content diversity and inaccurate physics simulation. And there are promising signs in both directions. So for example, the InfiniGen work that I showed can generate photorealistic 3D worlds. And at the same time, improvements in GPU accelerated physics simulators are making contact simulation more accurate. But more research is needed to truly unlock simulation as a scalable source of data. My goal would be to design these scalable sources of data, like building pipelines to turn vast amount of human videos and simulation interaction into training data for generalists. To conclude, the very word robotics was coined by Isaac Asimov 80 years ago, where he was envisioning a future where machines would do the work to sustain life and humans would do the work that makes life pleasant and worthwhile. My research in bringing foundation models to robots has moved us closer to the vision, but we are very far off, and a lot of challenges remain. I believe closing this gap is one of the most inspiring scientific challenges of our generation, and not a single person, a company, or a field could solve it. It would require collaboration across fields of robot learning, computer vision, human-robot interaction, control theory, sensing technology, and beyond. And I want to build a research program at TTIC along with great collaborators to truly take on this challenge. I think building generalist robot may be a generational effort, but I can't think of a more exciting problem to dedicate my career. Thank you.